Let me welcome everyone on our bi-weekly seminar, Quantum Information Quantum Computing Seminar, and a short introduction of our speaker. So today we have Lluis Masanes from University College London, and he will tell us about conformal unitary circuits and toy quantum gravity. So Lluis, the screen is yours.
Okay, thank you very much. It's really a pleasure to talk in your seminar. I'm very excited with this research that I want to talk to you now. Okay, it's my favorite brand of research that I'm among all the things that I'm doing. But at the same time, I don't have much time to do it because I have to do other things with students and other people. So I actually haven't thought about it for a while. Okay, but I think it's beautiful. Okay, so yeah, so this is the outline of the talk. Okay, so I'm going to introduce the concept of discrete conformal field theory in 1+1 dimension. Okay, this is based on what I call the discrete conformal near group. Okay, so it's an algebraic structure that it's almost a group, but yeah, some elements are not invertible. Okay. And then I will show you how to construct representations of this discrete conformal near group based on dual unitaries. Okay, I will also explain what is a dual unitary. Okay, later I will show how you can construct something like would behave like the ground state of the conformal field theory, in the sense that it has algebraically decaying correlations, logarithmic entropy, and so on. And later, once you have all this structure, okay, so this you can see that although it's a discrete model in a spin chain, okay, you have a lot of the features of conformal field theories in the continuum, okay, so you can talk about critical exponent, scaling fields. Sorry if you're not familiar with this, I'll try to explain it later. But many of the mathematical structures, not all, but many of the mathematical structures and the physical behavior of conformal field theories in the continuum is also recovered in this formalism of discrete conformal field theories. Okay, so once you have something that is a discrete version of a conformal field theory, you can do also like discrete holography. So you can use all what we know about holography, which is not much in my case, but I'm learning. Okay, so you can interpret the physics of a 1+1 conformal field theory as a theory of gravity in 2+1 dimensions. Okay, I'll try to explain this if you're not familiar. Okay, so and with this very simple framework with quantum circuits, tensor networks that I'm going to introduce, that is very discrete. So it's very from people that have quantum information perspective, it's more easy to understand that conformal field theory in the continuum. So for this very simple framework, you can understand gravitation, some phenomena like gravitational time dilation, black hole formation and dynamics, Hawking radiation, etc. Now, I don't know if I will have time to explain all these things, but let's have a try. And of course, please ask me questions, okay? Ask any questions. Good. Yeah, so maybe I can say that the advantages of this discrete over the continuum framework for conformal field theories and the ADS CFT correspondence is that in this discrete case, you can have full mathematical rigor. You don't need to do path integrals and things like that. You can also consider the possibility of simulating in a classical or quantum computer. Everything is finite dimensional. And also there are some phenomena that can be more transparently understood in this model than in the continuum holography physics. Okay, so let's introduce this discrete version of conformal field theories. First of all, so that we can understand the analogy, I'm going to explain to you what is the conformal group in the continuum, but in 1+1 dimension. Okay, so we are in the two-dimensional Minkowski space, okay? And these are our coordinates. By the way, do you see my pointer moving? Excellent. So these are the coordinates of Minkowski space and time, if you want. And a conformal transformation is any transformation, any map, okay, that maps these two variables to these new variables. If the transformation, so in differential geometry, when you do a change of variables, you also need to change the metric, okay? And this is the rule for changing the metric. The metric is Minkowski in the original variables, and in these new variables, we impose that it is proportional to Minkowski. So this is a number. This omega is a number that can depend on the position on the point of Minkowski space. Okay, so we say that a transformation is conformal if it preserves the Minkowski metric up to a factor. Okay, a factor that has to be positive. Okay. Good. So then you say, okay, so this is the definition of conformal transformations, but we want something more tractable, okay? So what is the solution to this problem? What are the maps from the x's to the z's that satisfy this constraint? And the solution is very simple. It just says, okay, so define the light coordinates, okay? This is the light coordinates for x0 and z1, and these are the light coordinates in the other variables, okay? And once you write everything in light coordinates, in the plus minus coordinates, then a conformal transformation is one that maps the coordinate plus to the coordinate plus, and independently maps the coordinate minus to the coordinate minus. Okay? So, yeah. And these functions can be arbitrary as long as they are smooth and invertible, which is equivalently to say that the derivative is positive everywhere. Okay. So yeah, so from now on, we can forget about all this if you want, and we can concentrate on this structure. Okay. Okay. So this would be an example of a transformation that could be a map on the coordinate plus or the coordinate minus, and is positive everywhere because yeah, the derivative is positive everywhere. And yeah, so it's doing some sort of contraction here around the origin, just to have an intuition of what this function is doing some sort of contraction, and it's more or less the identity far away from the origin. Okay, it's a contraction because we see that here the range in this flatter area, there is more in the x-axis than in the vertical axis. Okay. Okay, so good. So yeah, every function f or g defines a pattern of local dilation and contractions, because this can change everywhere. This is a contraction in the origin and its identity everywhere, but it could have dilation far away on the right or far away on the left. Okay, good. So now let's make a discrete analog of this. Okay, so I'm going to consider this is really not a function, because we have here that the point 2 is mapped to more than one point. Okay, so we can see a set theoretic version of this function, which is not a function. It is, let's call it a pattern of local dilations and contractions. Okay, this particular pattern of local dilations and contractions is represented here. Okay, so -3 goes to -3. -2 goes to -2, but also -1 and 0 go to -2, okay? And so on. Okay, I know that this doesn't make much sense, but it will be more clear when so this is just a pictorial idea, okay? Okay, so now later I'm going to precisely define these discrete conformal transformations. But before, I need to define dual unitaries. Okay, so this is a unitary acting on two spins. Okay, we could consider that this is the input. On the bottom we have the input, and on top we have the output of the unitary acting on two spins. And we put the arrow so that we know which indices are where. Okay, for instance, the arrow is useful if I want to write the transpose of this unitary. I can write it with the arrow pointing down. Okay, because we have flipped the top indices to the bottom with the bottom indices, okay? And if I want to conjugate this unitary with the swap operator, is basically moving the arrow from the right to the left, okay? And we also will use the dark shading to denote complex conjugation, okay? So then the Hermitian conjugation, which is transpose and complex conjugation, it's represented like this, okay? And unitarity, the familiar unitarity condition is this product of matrices equals the identity, okay? This is standard tensor network notation. And this condition, as you know very well, this condition is equivalent to the other, okay? So U times U dagger is the identity, and this is equivalent to saying that U dagger times U is the identity. Now, in order to define what is so this is what is a unitary. A unitary is a four-legged tensor that satisfies these constraints, okay? Now, in order to define what is a dual unitary, I will understand this condition as unitarity in the time direction. And then I can define unitarity in the space direction, which is defined in the natural way, okay? So when I now I do, what is Hermitian conjugate in the space direction? So it's something like this, right? It's not the transpose, it will be, in a sense, it will be the swap operator, okay? Conjugation with swap and complex conjugation, okay? So this is what we have here, okay? So this product is going to be, let's say, the spatial identity, okay? If you want to understand in the time picture what is this operator, this would be some sort of a not normalized projector into the maximally entangled state, okay, this structure, okay? It's just contracting the input indices with the output indices. And this
Can you please say again what was the meaning of the arrow? So I mean the position of the arrow.
yeah, so the arrow, so we have four indices here, okay? And the arrow just tells me which index is 4, okay? For instance, if I take this box and do the transpose, change the upper indices by the input indices by the output indices, this is basically inverting the arrow, right? Can you see my hand? Can you see me?
Yes, I can see you.
Oh, okay. So this is like the transpose, and this will be the spatial transpose or conjugation with swap unitary, okay?
Okay.
Is that clear?
Yes.
Okay, so this would be like the unitary condition in the space direction. Okay, and yeah, so there is a lot of research in dual unitaries. It's a hot topic because you can do lots of mathematically rigorous stuff. And yeah, there is, yeah. Okay, so let me maybe tell you what this, so we have a unitary, you know very well what is a unitary. Let me tell you an equivalent way to understand the space unitarity in the space direction condition, okay? This can be under, so let me call this unitary U, okay? So now I have an operator on two spins, which is A on the left spin and identity on the right spin. And then I conjugate it by U, okay? So if U is a unitary, then in general we'll have a general, okay, so yeah, so forget the cross. So in general, you will have a linear combination of terms of this form. You know, the terms that are non-trivial on the left spin, the terms that are non-trivial on the right spin, and the terms that are non-trivial in the left and right. By non-trivial, I mean traceless. I mean orthogonal to the identity. Okay. So this will be a general. However, if in addition we impose that U is dual unitary, not just unitary, but dual unitary, then this term disappears, okay? So this is the meaning of dual unitary. And what are the physical consequences on that? So it means that when we start an operation with an operator on the left spin, it will evolve into an operation that will have non-trivial support on the right spin. This is non-trivial on the right, this is non-trivial on the right, okay? And there is no trivial term on the right, okay? So in the left can be a superposition of trivial and non-trivial, but on the right is always non-trivial. So it's like if we have operator on the left spin, if we now evolve it in through a circuit of dual unitaries, it will evolve into a linear combination of operators on more and more and more and more spins, but always these terms of the linear combination always have a non-trivial support on the rightmost spin of the light cone. Okay? So in a way, these are particles that move at the speed of light, in a sense. Okay? And the same, you can prove the same from if you start with a spin on the left, okay? That it will generate a particle, the dynamics in a dual unitary circuit will generate a particle that I mean, the dynamics can be chaotic in the sense that an operator acting on a single site will evolve into a complex linear combination of operators acting in many sites. But all these terms have non-trivial support on the left, okay? On the leftmost spin of the light cone. Okay?
Sorry, can I ask, like, I guess you can have similar situation also with non-dual unitaries that, you know, you construct such a arrangement of unitaries and just on the boundary you're gonna
Yeah, so
I guess
what
you
you're
can cook up such examples, right? Or
I would say no. I would say that of course you always have the light cone structure.
yeah.
Okay, but when this operator evolves after some time into an operator here, it will be a complicated, in general, a complicated linear combination of operators, but some of the terms of the linear combination will have identity here.
Mm-hmm.
Also,
Okay,
dual unitaries are also unitary, okay? So it's maybe the case that you can cook up turns out to be a dual unitary.
Okay, so you would say that if this type of condition holds for all input operators on this red vertex, then this is equivalent to
Yes,
okay.
that's it.
Okay.
Okay, so let me explain what is the core idea of this framework, okay? So, okay, so here we could understand that this is the evolution operator of this circuit, okay? So give me any dual unitary, and I can construct a circuit with this pattern of, by putting, so all these tensors are the same tensor, except that maybe we are flipping its legs up and down or left, right, and maybe we are doing complex conjugation, okay? But this all follows from a single dual unitary, okay? So if I construct this evolution operator, for instance, where now I can put, now I can put, this will be my input state, the state will be in the bottom, and it will evolve onto the top, okay? But if I act with this operator, okay, this is an operator, well, actually it's an isometry because it has 3 input spins and only 1 output spin, okay? So yeah, it's an isometry, but well, it just maps my spin chain to a spin chain, another spin chain that has 2 spins less, okay? And now the dual unitary structure makes that this unitary is the inverse of this, okay? You can see that, but maybe I can just go back. It's just this condition, right? So the dual unitaries, when you do tensor networks, it doesn't matter if you twist the tensors in any way, if you rotate it. The only important thing is how you connect the links, okay? So in this case, this connection is such that this is the revision conjugate of this, so then will be the identity, that this product of tensors. So I substitute this tensor by the identity, okay? And then here I have a similar situation. This is the inverse of this, so I can substitute it by the identity. and this is the inverse of this. So I can substitute it by the identity, and so on and so on. So I get this, okay? So this is, again, so this gives the impression that we have done a contraction of space-time in the direction plus, the light coordinate plus, okay, that goes in this direction. Okay, so this is not anything rigorous, it's just to give some intuition for what comes now. Okay, so just is the idea that certain operators will act by removing a band of space-time that is just diagonal. So it's basically doing a contraction on one of the two light coordinates. Okay, so now let me introduce the evolution operator of this theory and also the general discrete conformal near group. Okay?
May I have a question?
Yes, please.
You said this is evolution operator and we have some input state. So what is the setting? What is the Hilbert space actually? What we have
Sorry,
here?
Yeah, sorry, I've been a bit vague of that. The Hilbert space of that is a spin chain. Okay, so you have n spins. The spin chain can be infinite or can be finite. And the local spin dimension is also arbitrary. Okay, is the same of the dual unitary that you have chosen. Okay, so for every choice of one dual unitary, we have a new model, a new representation of the conformal linear group. Okay, discrete conformal linear group. Okay, so these legs correspond to the indices of the spins of the spin chain, and it continues on the right, dot, 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 and on the left. So it's basically any size that you want. Okay, because of this structure, the size of the spin chain, if it's finite, it has to be multiple of 4, because the periodicity of this is every 4 spins, but this is not important, okay? Okay, so something that I'm going to do now is, actually should have started by this, I'm going to choose dual unitaries that have an extra symmetry, which is that the transpose equals the conjugation with swap operator. Okay, sorry, that's not very important. It's because then we can, the evolution operator, instead of having 4 layers, it only has 2 layers. Okay, so now I put 2 arrows because it's clear that if I rotate my tensor 180 degrees, okay, so if I do that, look at my hand, I get the same tensor. And this symmetry is graphically captured by this double arrow up and down. Okay. So give me any dual unitary that satisfies this condition, and then I can write one of these theories, okay, where the evolution operator, the one-step evolution operator is this, okay? So we are dealing with a theory that is discrete on space and is discrete on time. So dynamics is not characterized by a Hamiltonian, because it's discrete. It's characterizing by, let's say, if you want, you can call it a Floquet unitary. Floquet unitary, okay? So this circuit, it's going to be the one-step evolution operator that maps, this is a space-time diagram, so it maps points to the future, okay? Just by definition. And if you want to understand it in terms of the coordinates f and g, it just increases f and g by 1, okay? This is also going to be very familiar. This is just the shift to the right. So it moves space-time points to the right. And in terms of the f and g functions, it implements this transformation. Okay, so until now this is very trivial. That has nothing, there is nothing conformal here. We just have an evolution operator that you can have in all Floquet systems, right? Now let me introduce the generators of these discrete conformal transformations. Okay.
Sir, can I ask a question about the
Yeah,
previous
please.
slide? Can you just move back, just maybe one back, or okay, no, I meant, okay, like when you described the how I should imagine swap or like shift operation.
Sorry, yeah, this.
Right. So I don't fully understand like why I have. Yeah, like can you give intuition why? Yeah, why the shape sort of behaves like this? Like I have like vertical points at the end, and the end, at the top and at the bottom, or
Yeah. Yeah, this would be this is a tensor, okay?
Yeah.
This is the input, these are the links to the input indices, okay? So you put states here, okay? A state would have all these inputs, okay?
Okay, it's like
Yeah.
it's just to indicate the legs of the tensor. Okay.
Yeah. Exactly.
Okay. Sorry. Okay.
This, if you want, is sort of identities.
Sure. Okay, thanks.
Okay, so let us characterize these generators of this discrete conformal near group, and then you can see that what we do is basically a discrete version of this F and G that you have seen, okay? So I want to, first of all, I will just write them in front of you, and I will say, okay, so this operator, which acts on the spin chain, okay, sorry, one thing, in order to introduce the generators, it's easier to deal with the infinite spin chain, okay? You can have a set of generators with the finite spin chain, but they are a bit more complicated. So for the sake of simplicity, I'm going to consider only the infinite spin chain, okay? So these dots imply just going infinite to the left and infinite to the right. These are identities, okay? This operator acts as the identity. By the way, Q is the dimension of the local Hilbert space, okay? And we put here Q so that this is an isometry, okay? These are identities, and beyond X, we just have this circuit, okay? This circuit, okay? If this was finite dimension, you would have two more inputs than outputs, okay? And this is due because this is a local contraction here. This is why it's called C. C is because of contraction, okay? But you know, because there are infinitely many inputs, spins, infinite minus 2 is still infinite, okay? But this is important because this is what makes the operator not invertible. Okay, so this operator has some non-trivial kernel. Is an isometry because of that. Otherwise, it would be a unitary. Okay, so the previous two operators are unitaries. This is going to be an isometry. Okay, and later I will show to you that what this transformation does in the Hilbert space is this space-time transformation. Okay, so this is a space-time transformation. So it's like it will shift all the points that are in this triangle of the space-time, the 1 + 1 space-time, are shifted in the minus coordinate direction, okay? And all these points that are white means that nothing happens to them. So it means that here, around this diagonal, you have a local contraction, because if we are moving some spins in this direction, and these spins are not moving, it means that some spins here are disappearing, okay? If I'm moving this here, and the spin that is here is not being moved, since at the end we have a spin chain, some spins are disappearing. This can also be represented in the FG notation, okay? So here, the F function corresponding to this would be, it's G because it's the minus. The G function would be this one, okay, corresponding to this space-time transformation. Sorry, I have not proved yet that this operator gives you this space-time transformation, but I'll do it soon, okay? It's simple, okay? This would be the same thing, but it's a local dilation, okay? So identities here, this circuit here, and here we are doing nothing, and here we are pushing all the spins to the top and to the left, okay? To the future and to the left. So it means that new spins have to be created in this line. And this is the responsibility of these two legs. These two spins are being created, okay?
Wait, one question.
Yes.
The object to the left depends on X, like the spin from which you start.
Yeah.
But I don't see the dependence in the right on X where it sits. Like in this figure that you say it's
yeah, sorry,
responds
yeah.
to the
Very
dilation.
good observation. Yeah, so this X means that for every X we have a different generator.
Ah,
Okay, and here in this diagram, I chose X to be 0. Okay, so this is X. The point at which the dynamic changes is at 0 position.
in
And
the
at
X
this
minus
time.
coordinates.
Yeah.
Okay, okay.
And the same here. Okay.
Mm-hmm.
Yeah, so you're right. This equality is not an equality, it's just for when X is 0.
Okay. So this, okay, thank you.
Yeah, also this X is not, is maybe that's a bit confusing. This X is the space position. It's not the value of the X minus coordinate, okay? It's the space position. This is a operate, so these spins are different values of X. So this would be X, X plus 1, X plus 2, X plus 3. And but this is the spins, like the spins. We are not talking about live coordinates here. When we talk about spins, this will be at a particular time. At a particular time, you have a Hilbert space, and each spin has a different value of X. Okay. However, we will show that this map, when we want to map operators, it acts as moving the X coordinate, okay, and not doing anything in the plus coordinate.
Okay.
We will see this soon.
Cool.
Sorry? Okay.
Sorry, I said I'm happy. Thanks for the explanation.
Okay, good. So this is local contractions and dilations of the minus coordinate, and these are local contractions and dilations of the plus coordinate. Let us prove my claim, okay? Yeah, so let us prove that this does this transformation. Okay, so first of all, I define what is an operator into a particular space-time point. Okay, so this is take an operator that acts on a single spin and acts on the spin X. Okay, and now evolve it to the future or to the past, depending on whether t is positive or negative. Evolve it to the future t steps. Okay, if t is negative, pues is evolving to the past. Okay, so this is what I define by a operator acting on a space-time location. Beware that as an operator on space, this doesn't need to be single spin. Okay, if t is different than 0, this can be an operator. There will be some operator growth in general, and it will act on more than one spins. But I interpret it as, because it's the evolution to the future or to the past of a single spin operator, I talk about this operator being on a single space-time point. Okay, this is the same language than in field theory. Okay. Okay, so I'm going to show that when this operator is acted by this operator, it implements this transformation. Yeah, so the first I have to see, so I'm going to act with this operator on the evolution operator to the power of t times, okay? So this is, this is the evolution operator. Okay, maybe can I write? No, I don't have writing tools here. Okay, so this is the evolution operator. And now we are acting from the left. Left is the output space, so the top. On the top with this C minus operator. Okay, C minus was exactly this. Okay, where this is X. Okay, this spin is X. Okay, and now we can do the same operation that we did in the example I put, and this is the inverse of this. These dual unitaries are Hermitian conjugate of each other, so they cancel and you get the identity. And now these two unitaries cancel and you get the identity. Okay, so now I can just rearrange these tensors and shorten this connection, and then I have that I have commuted C on T, except that now C is, so this was the spin X, and now C is two spins to the right. Okay, So these are the algebraic commutation relations. So I can commute C minus with T, except that then X increases by 2 units. Good. Oh. Okay. So yeah, okay. So yeah, I have to prove my claim. So let's suppose that T is 0. Okay. So if T is 0, we have only X. What this is doing is so because T is 0, we are in this blue line. Okay. And let's suppose also that X is 0. Okay, we're here. So now no, sorry, X can be any value. So in the left of the blue line, this acts as the identity. Okay, so this operator A, when acts here, is not being moved. Okay, when the operator is on the right, it evolves one step to the future and one step to the left, which is this arrow. This arrow is pointing future and left, right? It's the diagonal in the minus direction. So we see that when this T is 0, this operator, the operator AX, then, because T is 0, when it's mapped with, when I sandwich this by this, I map it to the future and to the left. So then I prove this, that the map works as specified in this picture, at least in the blue line, because we are at time 0. Now, when time is not 0, I can use the commutation relations that I just obtained, and every time that, so if we have, let's say, 2 units of time, every time I commute the C with T, the X is moving to the right by 2 units. So then that explains why, if instead of at time 0, we are at some future time, then the threshold of the different behavior of the map moves to the right. Okay. So this argument shows that this operator maps operators at one space-time location into a different one based on this diagram. Okay. Now, just the final piece that we need is that, so we have proven this identity, okay? And we also, so this will be a contraction of the minus coordinate, and this will be a dilation of the minus coordinate. But you can choose, but these are at 0. And you can choose X. X doesn't need to be 0, okay? So I can choose this dilation and these contractions to be at any point in the minus coordinate. Okay, so by composing now different C's and D's for different values of X, by composing arbitrarily these different generators, I can construct basically any curve of this form. Sorry, this form, for example, this one, okay? So this is what I claim. This is what I claim, that these generators, these 4 generators and their complex conjugates, well, 4 for every value of X, okay? 4, but now you can change X. Just generate a group that it is a discrete version of the conformal group in the continuum. Okay, you can prove some facts, some mathematical facts about this set of generators, okay? Okay. Now, but yeah, this is not that relevant, okay? So maybe you want to see, for instance, what is a Lorentz transformation, okay? So a Lorentz transformation would be an operator that, yeah, maybe I can go, give me a second. Yeah, so as a Lorentz transformation is one that maps the black coordinates into the red coordinates, okay? So for the points that are in this axis are mapped to the future but the more to the right they are, the more to the future are mapped, okay? And here, the more to the left they are, the more to the past they are mapped, okay? So if I wanted to do a discrete version of this transformation, I could take the evolution operator and do like steps like this, okay? So this is what we do with the operator this is what this does, okay? This is like a discrete Lorentz transformation, and so this is for a particular value of the velocity of the boost velocity, okay? If I want to do a different boost, I would have to space more and more, I would have to put more identities between, so you know that this, we have C and C, so I would have to put, so this is like C minus 3, this is C minus 13, so I would have to space it more if I want a Lorentz transformation with a smaller boost velocity. Okay. Okay, well, this is, I just wanted to show a particular example that is familiar, but yeah, it's very complicated. But yeah, this will be a one particular Lorentz transformation. Okay, now
sorry, can I ask some fairly basic question? You said it's a near group, so some elements are not. So it's because
Yeah.
things are not invertible. This is
yeah.
Okay.
So some elements are such that when you multiply, let's say U and U dagger, instead of getting the identity, you get a projector.
Mm-hmm. Okay, so let's say you had yeah. Okay, so my question is as follows. So you had like this in the continuous case presentation of the conformal group in terms of those functions that that transform positive coordinates to positive coordinates, and likewise negative ones, and derivatives for positive. And then you were sort of arguing that okay, like the good discrete analog is those sort of relations that are also kind of, I guess, monotonic. So my question is like in that, okay, how to phrase it? So like I guess it would, like, can you define some algebraic object that sort of is defined irrespectively on the spin chains, and then what you have here is like a representation of this spin chain in this of this object in this specific spin chain. Yeah, that's my question.
Sorry, if I can define.
So can you define like some algebraic object, just
Yeah.
like conformal group, like sort of that encodes those discrete relations, perhaps, such that what you're describing here is actually a representation of this object.
Yeah. So this.
Yeah.
So you can do. So for instance, if now I've been doing manipulations abstractly. Okay, just by I've been contracting, for instance, in this type of argument, I've been contracting these tensors, but this works for an arbitrary dual unitary tensor. Once you give me one particular dual unitary, okay, for acting on a particular, on a spin of a particular dimension, then all these become operators on a spin chain, and these are all so these are all you know, operators acting on a spin chain, and I can multiply them as you apply operators, and if the spin chain is finite, then you have matrices. Is this what you asked?
So I was more asking like whether you can like define like algebraic structure without referring to spin chains at all.
Yeah. Okay. So like a group. A group. Yeah.
Yeah.
Okay, that's a very good question. And yeah, after I prepared this talk, which I prepared this presentation 1 year ago, I noticed this weak point, okay, that you just mentioned, and then I wrote exactly what you're saying, okay, but I cannot present it to you today because I'm not prepared with that. But yeah, so I just well, what I did basically is characterize the precise structure of these discrete functions G and F. Okay. So in the continuum, it's just any smooth function with positive slope, because if you compose smooth functions with positive slope, you get another smooth function with positive slope. It has all the axioms of a group. Okay. So now, what is the analog in this discrete case? So there is an algebraic structure, but I'm not explaining to you today.
Okay, yeah, thanks.
Maybe next time.
Yeah.
Okay. Yeah, so this, what I presented here is mostly about the representations of this structure in when you want to act them on a spin chain. Yeah, thank you for your question. Okay, so now let us see some properties of the of conformal field theories in this discrete version of conformal field theories. Okay, so when you a conformal field theory, you always define primary fields. Primary fields are transformations, are those. Okay. So yeah, let me go back to one thing that I missed. Okay, so here I claim that the operators that are in the left of X are nothing happens to them. Okay, so it's this white area, and operators that are on this spin to the right are mapped to, or at least from this spin to the right, are mapped to the future and to the left. Okay. However, what happens with these three spins? Okay, this is not evolution to the future. This is indeed evolution to the future. Okay, and here to the left. But with these three spins, we have something different. Okay. So yeah, the evolution is not going to map. So except for these 3 points, this operator takes any single spacetime point operator and maps it onto another spacetime point operator. But this does not happen in general for these 3 points. However, and this is the same in the continuum. Okay. However, we want to find the primary fields are those fields, those operators on a specific spacetime point that, independently on where they are always mapped to the same operator at another spacetime point. So even if they are here, okay, even if they are here. So then we need to find a condition for when an operator is, for instance, here in this spin, is mapped to itself, maybe up to a constant. Okay, so we define this completely positive map, okay, for the minus direction and for the plus direction, and then we find the operator, the eigenoperators of this completely positive map. Okay, and these eigenoperators are operators that, despite being on this point, are going to be mapped to themselves except for a constant lambda. Okay, so this is really analogous to what happens in the continuous. So then these eigenoperators are the primary fields, and the corresponding eigenvalues are related to the critical exponents that in conformal field theory are called scaling dimensions of the CFT. Okay, so there is this relation, and this will have to do with the correlation functions, okay, that we are going to see soon. So all this algebraic structure is very analogous to what you find in continuous conformal field theories. Yeah. So now what I would like to find is, so in field theory, you always work with the ground state or perturbations of the ground state, or maybe also the thermal state, but not much more, okay? And here, we don't know yet what is the ground state. Also, I mean, you know, what we have, the time evolution is a unitary circuit. Unitaries don't have ground states, okay, or thermal states, because all the eigenvalues are ordered modulo 2 pi, okay? So we cannot say that one eigenvalue is smaller than the other. That doesn't make sense, okay? At least in general. Okay, so there are, so yeah, forget what is written here, okay? Forget this. So what I would like to find is a state that behaves, that has the same physics as the ground state in the continuum, okay? And let me first start by describing what I call a regular tensor network state. Okay, so these are two examples of regular tensor network states. So this, although this looks like a quantum circuit, but it's not a quantum circuit. It's actually a quantum state, because and the spin. So the spin chain would be this blue line, and the free indices would correspond to all the spins. Okay, this is the spin 0, the spin 1, the spin 2, and this, I think it has 20 spins, maybe. Yeah, 20. Okay, so this would be spin 19, right? And yeah, with periodic boundary conditions, and all the tensors are contracted except for these free legs. So this is just a vector in a Hilbert space of dimension q to the power of 20. That's all. Okay? And this is another, so here we also interpret this as periodic boundary conditions. Okay? And this is just another way to write a tensor network state, that this will be the ground state of the conformal field theory, like approximately. Later we will see how these states behave, okay? But the nice thing about these states is that it's very easy to calculate. Yeah, okay. So first, let me go to a bit of holography, okay? So in holography, okay, so first of all, let me say that there seems to be a bulk here, right? There seems that although we are dealing with a one-dimensional system, there is this internal surface here and also here. This looks like flat, kind of, and this looks like hyperbolic, kind of, like the hyperbolic disk. Okay, the Poincaré disk, maybe it's called. Okay, so, and in holography, now I'm just going to mention an idea from holography that will inspire us to do things in these discrete theories. So you can endo, so the internal, so if you have a quantum state of these spins, okay, so let's forget about the interior, this surface. I just put a curved surface, but let's forget about this. If you have n spins here, you can calculate in a pure state, okay, you can calculate the entropy of this region, okay, I take the reduced density matrix of this region, and I calculate the von Neumann entropy. And then this entropy should be equal, this is the Ryuta-Kianagi prescription, to the length of the shortest path connecting these 2 points. Okay? And if you do that, so here we have done that from the region, from the interval from x to y. But if you do this with all the intervals of all the spins, okay, then, and you can calculate all the entropies, then in some cases you can reconstruct the full geometry of the bulk. Okay, so the same happens for these regular tensor network states. It turns out that, yeah, maybe yeah. So the fact, let's go here. The fact that this is a dual unitary, so you know that a unitary, if a unitary acting on a single spin can be understood as a maximally entangled state of 2 spins, right? So then, because this is dual unitary, it means that if I take this unitary, okay, sorry, this should be a box, okay? If I take this box and consider the entanglement of these 2 pink spins with respect to the black spins, it's also maximally entangled. So it's, the entropy is 2 log Q. And if I want to look at the entropy of a single spin, is also 1 unit of log Q. Okay. Now, if you want to deal with more general tensor networks like this, you can prove that for all these tensor networks, like these 2 examples and this example, for instance, the entropy of these 5 spins will be equal to the length of the shortest path. And what is the length? To calculate the length, I substitute each box here by a cross, and then the shortest path is the one that cuts the least number of lines. Okay, so this path cuts 1, 2, 3, 4, 5 lines. And you cannot find another path cutting less than 4 lines. Okay, and you can find paths that cut more than 5 lines, but not less. Sorry, 5, I meant, not 4. Okay, and if you calculate the entropy of this state for any dual unitary, no matter what dual unitary you choose, it's always going to be 5 units of log Q. And this is just another example, but it works for any region. If I am interested in this region, here the entropy is 2 units of log Q, because the shortest path cuts 2 lines. Okay, so here, I mean, I'm not proving this, but if you calculate it, it's what you obtain for lots of examples. Okay, and for every example, all the regions, all the subregions, all, let's say, connected subregions, contiguous sets of spins. Okay. Another interesting fact about these regular tensor network states is that you can calculate the dynamics. Okay, so I said before that this is a state, and this is the evolution operator. Okay, so now let's apply this evolution operator on this state. And in order to do it slowly, I will apply first this layer of unitaries, and second, this layer of unitaries. Okay, these are the, let's say, the unitaries, let's call them even. This is T even and T odd. Okay, so T is the product of T even and T odd. So if I apply with only T even, because this is the 0, so this has to be connected to this leg here. So I just, this layer is just this layer here, okay? Which is evolving my state to another state. And now these 2 unitaries cancel, because one is the Hermitian conjugate of the other. These 2 cancel 2, these 2 cancel 2, these 2 doesn't cancel, these cancel again, and you end up with this. Okay, and this is half a step of the time evolution. We need to apply the other half. So I apply the other half, okay, and then it transforms into this, okay? And you can continue evolving the state. Sorry, yeah, sorry. There should not be this this paper here, okay? So you just have an evolution, and it's just a periodic. It does something like this, okay? It's a periodic evolution. So this is like the evolution of the geometry of this space-time somehow, okay? And also another thing that we observe is that these regular tensor network states are they have regular dynamics, okay? So you could choose a dual unitary that is chaotic, okay, that has a spectral form factor of a random matrix, okay? However, in the evolution of the spin chain with these dual unitary circuits, there will be subspaces with these regular tensor network states that would evolve not chaotically, okay? And this is what people call quantum scars.
Luis, I'm sorry, but would you be able to, I don't know, conclude in, say, 10 minutes?
Yeah, sorry. Yeah.
Mm-hmm.
Okay. So, yeah, I'm going to conclude. So yeah, you can find this is the ground state, and you can calculate correlation functions and entropies, and you get the same ones of the than in the continuous case, like what you would you get discrete versions of like this logarithmic entropy, these algebraic correlation functions. Okay, so I almost have time to introduce you with these models that are discrete conformal field theories. Okay, I didn't have time to move to holography, to move to this toy theory of gravity, but at least you now have the formalism to do that. Okay, so I hope you liked all this. Thank you very much.
Okay, thank you very much. So perhaps we can organize a series of lectures for you.
Yeah.
About these things. It seems that you have a lot of slides. So, are there any questions? Not from Michał. Okay, Michał is very welcome to ask questions, but maybe some other people also have them. Okay, Wojtek.
Just out of curiosity, this periodicity of evolution, is it characteristic only for such particular state or for other states also?
Yeah, Yeah, and it's also very interesting because it turns out that when you move, let me do it. Just 1 second. I find the right. So when you put also one particle, I haven't explained what is to put a particle. Okay, so these states, these tensor network states, when don't have particle in the gravity toy theory, are interpreted as just pure space-time without matter. Okay, and this evolves regularly. Okay, and if you put one particle, the particle bounces from one corner to the other. Okay, and back and forth. Okay, so you can also put one single particle and then you have a periodic state, okay, a regular state. But as soon as you put two particles, you enter in a chaotic regime, okay, and this is interpreted as the formation of a black hole, okay. So you have that that you will explore all the Hilbert space. Basically, you never come back. Maybe you will have some quasi recurrences, but you never come back to the original state. Okay, so so the answer is yes. The answer is there are states. The majority of states are not periodic, are chaotic, but there are some periodic states, and they have a gravitational interpretation. The periodic states are correspond to intergravity sites to spacetimes with 0 or 1 particle.
Okay, thanks.
Okay, Michał?
I mean, okay, I must confess that I got lost in the second part of your talk, but just I maybe got intrigued about this last explanation. So can you maybe technically explain what you mean that the evolution when you put like two excitations, whatever that, okay, you didn't explain technically what this means. So what like what technically is taking place? Like, do you have some
Absolutely,
let's
absolutely.
say like what let's say what is the Hilbert space that we are exploring, and like do we fill in the whole like all like epsilon neighborhood of every possible state, or are we in some torus? I don't know, I'm just like guessing.
Well, the numerical calculation, I did some numerical calculations, okay, and what I did is consider the simplest spacetime, which just has a boundary of 4 spins, okay?
Okay.
And I consider the state with 0 particles. This is basically a local operator acting on 1 spin. And this is 2 local operators acting on these 2 spins,
yes.
Okay? Now, what I take is I take each of these states and I evolve it in time. And I look at the dimension. So I just take state at time 0, state at time 1, state at time 2. So I generate a sequence of states, and then I look at the dimension. So for instance, I generate a sequence of states up to time t, and then I look at the dimension of the Hilbert space that they span, the subspace that they span. Okay?
So like a Krylov, sort of like maybe Krylov type of ideas. Yeah, okay.
Yeah, okay. So if I do that for, and these are exactly these plots. If I do that with, so here you can see if the local dimension of the spin is 3 and 4. Let us just look at 4. If the particle is 0, you have this blue line. It's a periodic state, but it has period 2. Sorry, it has period 1. Okay, it's an eigenstate actually. So it's this blue line. If you put one particle, then you have a periodic state. So the Hilbert space generates a subspace of dimension 2, and it stays there.
Yeah.
It never goes beyond dimension 2. But as soon as you put 2 particles, or you just choose a random state of 4 spins, you go up to the maximum dimension. Okay, so that's what I mean by...
I see. So you'll be... Okay, you'll have plenty of linear independent state in the course of the...
exactly.
Okay. Okay, thanks.
You're welcome.
Okay, so maybe the last question from me. So can you say again what was the motivation to study this discrete field theories?
So I was studying I was studying the historical evolution, let's say, was I was studying papers by Prosen on dual unitaries. And then I said, so in the past, I already worked in, quantum cellular automaton and things like this. And quantum cellular automaton, when you do some sort of scaling limit, so you take the continuum limit, they have Lorentz invariants, okay? But if you don't do the limit, they don't have any Lorentz invariants. So I wanted to find some sort of discrete, exact Lorentz invariants, not approximate, but exact, okay? And I said, okay, this dual unitary seems pretty Lorentzian, because you have a unitary that it is a unitary in space, but also in the time direction. And I always started playing from there. So first I just wanted to build Lorentz transformations, and later I realized that for free, I also had scale transformations.
But I mean, so are you able to predict some phenomena which, I don't know, don't exist or are unknown in the non-discrete case?
That is not known in the continuous case?
Yes.
So for the, well, I would say for the case of just discrete conformal field theories or conformal field theories, I would say no. Maybe here you can find more models that you can calculate better, okay? But no. For the holography thing, of course, this has to be understood as a toy model, but for instance, this creation of black holes, once you put more than one particle, and I define a black hole as a region of space-time where the time evolution explores all the Hilbert space, okay? With this definition, I think this is something, I could be wrong, but this is something that has not been obtained in the continuum.
Okay. Okay, thank you, Lluis, once more for your nice talk. And well, this concludes the seminar, and we see each other in 2 weeks. And the next speaker will be Alexa Salavrakos from Quandela. She will tell us all the secrets of the company. So, thank you. Bye bye.
Thank you very much.